We would like to welcome you to this webinar, which is part of the ongoing series of professional development webinars conducted by the ITEEA. This webinar describes an initiative that has the potential to be transformative in the way teaching and learning in technology and engineering education is conceived. It is a grandiose claim, but one that we hope you will resonate with once we conclude this presentation. My name is Michael Hacker. I taught secondary school technology education for 20 years, served as a state supervisor for Tech Ed in New York, and for the past 2 decades have co-directed the Center for STEM Research at Hofstra University on Long Island. I will present a brief overview of EFA, then we will watch a 10-minute introductory video. Following that video, 2 expert middle school technology and engineering teachers will discuss their classroom implementation. Matt McGuire teaches in Elwood, New York, and Matthew Plummer teaches in Davidsville, Pennsylvania. The EFA project has been funded by the National Science Foundation. EFA stands for Engineering for All. The project developed 2 6-week curriculum units that are situated in authentic societal contexts. One is in a food context, titled Vertical Farming, Fresh Food for Cities. And one is in a water context, titled Water, the World in Crisis. Student and teacher guides were developed for both units, and the units have become part of ITEEA's flagship Engineering by Design curriculum. Embedded and performance-based assessments are included within the materials, and research was conducted about the feasibility of implementation in technology and engineering middle school classrooms, and about the pedagogical content knowledge teachers need to teach design. EFA materials were tested for feasibility in 22 middle school technology and engineering classrooms across the country with 755 students, and revised based upon teacher, student, advisory board, and evaluator feedback. Our project's vision is to promote the potential of engineering as a social good, in addition to being a career path. To open students' eyes to the role engineers play in addressing important global and community-based issues and problems, and to instill in our students a predisposition to want to make a real difference in the world, and a sense of confidence that with continued study they will be able to do so. Pedagogically, we're asking our students to solve design challenges in contexts like food and water that relate to problems facing many people in our country and throughout the world. The project is also unique in that we've identified and are revisiting a set of overarching technology and engineering themes in both contexts. These overarching themes are repeatedly referenced in the literature, and they contain ideas about design, modeling, systems, resources, and human values. Finally, we are using informed design methodology as the core pedagogy. Informed design is a pedagogical approach that engages students in the development of knowledge and skills relevant to the design challenge before they begin designing. It's not dissimilar to accepted design methods. However, EFA students create design solutions informed by the new knowledge and skills they learn, rather than through trial and error gadgeteering. Knowledge and skills are learned just in time through pre-designed tasks called Knowledge and Skill Builders, or KSBs. The KSBs provide hands-on, inquiry-based learning about STEM concepts that underpin the design challenge that is presented. The curriculum structure is the same as other ITEEA Engineering by Design units. Both EFA units begin with a component called the first 4 days. which is designed to accomplish 3 learning goals: to position design activities as central, and to introduce the informed design process to our kids. The first 4 days also serves to introduce students to the use of knowledge and skill builders as a means to inform their base of relevant knowledge before they engage in the design challenge. And it serves to measure students' prior knowledge about the unit's material through the use of a pretest. The second component comprises the knowledge and skill builders. Matt and Matthew will give examples of these in context. And the third component is the Grand Design Challenge. Both units conclude with students engaging in a capstone design activity that requires them to apply the knowledge they gained through these KSBs. Now let's look at a video of our students in Oregon and North Carolina as they move through their first EFA experience.
Some of the greatest challenges we face as a global society relate to lack of availability of fresh food and clean water. Today, 2 billion people lack adequate access to clean water. It's one of the greatest political, social, and health challenges of the 21st century. Although water is abundant on Earth, less than 1% of the planet's water is fresh water in lakes and rivers, and that water may not be clean, and it may be far from the cities and homes where it is needed most.
Worldwide, about 784 million people don't have access to what we call an improved water source. So an improved water source would be something with a little bit of engineering around it. In addition, about 1.2 billion people who use improved sources have contamination in them. So in total, it's about 2 billion worldwide that don't have access to microbiologically safe drinking water. So I work in places to try and work with households to either get access to a safer water supply or treat their water at the household level.
Through the National Science Foundation-funded Engineering for All project led by Hofstra University, in collaboration with the International Technology and Engineering Educators Association, students in Carolyn Banks's classroom at Spring Hill Middle School in North Carolina are learning how engineers like Danielle help bring clean, safe water to a thirsty world.
When these kids leave school, they're going to have to solve the problems that we didn't solve. Food scarcity, water scarcity. Engineering for All engages kids in understanding really global problems, real-world problems, and learning the skills that they need to define a problem that they can solve.
Does this system have an output?
And develop the skills to solve that problem.
It would be what?
Clean water.
It's been awesome, especially with this class because they're excited about learning, and if they're motivated and they have hands-on, something they can touch, feel, manipulate, they enjoy it more. We also make it relevant to the real world, like this project. They really buy into it.
It just seemed different than all the other classes because we get to do experiments in this class and we get to learn different things than what we would normally learn in math class or science class.
You actually get to do stuff hands-on, and I think you learn a lot more because I know I learn a lot more if I get to touch stuff and see stuff.
Water scarcity is a global problem, and Carolyn Banks' students have chosen Bangladesh as a case study.
The final grand challenge is when they actually use the materials that are native to Bangladesh, and they make a water filtering system that the natives or the residents can use to filter their water.
We're trying to make a portable and convenient filtration system for Bangladesh because that's part of our project is to make a filtration system for Bangladesh because they don't have any clean water.
So filters work in a number of different ways. The first way they work is just the way a strainer would work. Like if you put your macaroni in a strainer, the biggest particles are going to get captured right at the top, and they're going to stick there and they're going to make a layer. And then as you then go further down into the filter, the smaller particles might get trapped in the pore sizes.
Each one we're going to put something different like charcoal, fine sand, and coarse sand. And then we're going to put the water through it and see how it filters the parasites out.
You need different types of filter material to filter out physical and chemical contamination, so the biological contamination and the chemical contamination.
We're trying to purify water that has metal in it, like lead, stuff like that. And we're trying to keep it from getting into people's body systems so they won't get sick.
They really have gotten it, that this is for real. You know, this is not something my teacher's making up. I'm really taking part in a project that's going to affect somebody's life.
You learn how to help people in this class. Like, you learn how to make water filters for different people who don't have water when we're so careless for our water.
Engineering for all students are also taking on a second critical issue, food scarcity. Today, 1 in 8 people do not have the food they need to thrive. As the world's population rises, the problem is only getting worse. Meanwhile, the amount of land that's suitable for growing food keeps getting smaller. Cutting forests to make room for more farms could devastate rare natural habitats and make global warming worse.
These two problems are closely related. In order to grow food on a farm, it takes a lot of water because water flows through and out.
When we think about a child's health, we're not just thinking about water, we're also thinking about food.
One solution, vertical farming using hydroponics, growing crops in water without soil.
The water comes from this tank, which if you open up, there's just a whole bunch of water.
In hydroponics, it's much more conservative of the water because the water keeps circulating.
Hydroponic beds can be built vertically onto the sides of tall buildings, so there's no need for farmland. And food can be grown right where it's needed.
How to get the water in and out so the plants can have water.
In Stephen Hayner's class at Claggett Creek Middle School in Oregon, students participating in Engineering for All are discovering how vertical farming can help feed the world.
This one actually brought a real-world problem and gave the kids an opportunity to try to solve a real-world problem. And I thought that was really interesting for them to move into. When it comes to urban farming, most of the kids learn that there's just not much space available in big cities. And so in order to have farm and grow plants in there, you got to think about new methods of growing.
They'll have like a drain or something.
I think it's definitely getting a lot harder to feed the more people on the planet because the population is definitely growing and it's just going to continue to grow. And with the hydroponic systems, I feel like you'd have a wider variety of food that you can plant yourself at home. So you will just have like a better like eating supplies. Plus it's more food and it's like faster and more efficient.
And what is the size of the cups?
2 inches.
To learn how hydroponics works, students are building their own hydroponic systems. Teams start by drilling holes for the cups that will hold their crops.
Check the measurements. 29.
They prep the tubing that will keep the plants watered. Another team is building the structure that will hold the finished growing tray.
1, 2, 3. Sorry, you put that on and I'll put the
They
lid on.
put it all together and then they are ready for the grand challenge, designing a vertical farming solution from scratch, using an informed design process to apply math and science to the technical and engineering problem at hand.
All the water just kind of goes all the way through the piping.
They were given some type of question that they had to solve. They'd come up with ideas and design prototypes. After they design a prototype, then they would go ahead and analyze their prototype and look at some data, make changes to their prototype, and in the end see if it actually worked.
Our design, it rotates like a Ferris wheel right here. And then it holds removable plant boxes. It dips into the water. It's on the north side for the maximum sunlight, and it's an ebb flow system. This is the greenhouse, so after that's where we do our harvesting. And this is what we use to take the plants on and off the side of the building so we can plant them and harvest them and re-put new plants on. The food is sold to the residents at this fruit stand, and residents now have access to fresh local fruits and vegetables.
This really opened up their eyes just to the idea that there's more opportunities in engineering. I always tell them that if they find something they like, there's an engineering career for it. And so they learned about agricultural engineers, which is something completely new to them. They didn't know that there was a field out there like that.
In conclusion,
we support Engineering for All due to the opportunity it provides our kids here at Claggett Creek. This specifically allows us to work collaboratively to identify local issues, problem solve those issues, and identify real-world solutions.
By using these ideas along with engineering and science to solve problems, kids learn the ideas much more deeply. And furthermore, they really develop a mindset that they can solve problems, that they can even address some of the world's biggest problems, and they can have success.
Engineering is problem solving. It's not kind of core research like what's some of the physics, like how's the universe built or all of that. But it's more about we need something and we'd like to get there, so how do we do that? And I think it's really nice with engineering when you see the tangible results.
Once the plants started to grow, we didn't want the light to burn them. So we have this nail up here and a rope. So what we do is we can lift it and we can tie it back on. I didn't know much about hydroponics until we did this, and it really opened up my eyes on how we need to do other stuff to help other people, because you don't really think about it.
This is what we did. This is what we came up with. This is what kids our age are thinking of. We can actually do this. It was just a proud moment. We were just very excited of our idea.
I'll do this one.
Students in Engineering for All classes are designing solutions to important community and global issues.
Right there, yeah.
Through their engineering design activities and continued study, these students will be prepared to make a real difference in the world.
All right, it looks good.
Hello everyone, my name is Matt McGuire and I'm a technology and engineering teacher from Elwood Middle School in New York. Today I am going to be sharing an overview of the food unit from Engineering for All entitled Vertical Farming Fresh Food for Cities. This unit is made up of several different parts, starting with the first 4 days that Michael had previously mentioned. The first 4 days can be used at the beginning of this unit to give students an overview an introduction to the informed design process and the organization of this curriculum. The food unit itself is made up of these 5 KSPs, which are knowledge and skill builders, which all lead up to the grand design challenge in the end. The first KSP is an overview of some of the food shortage problems around the world that is the driving idea behind the curriculum, as well as the overview of what hydroponics is itself. Some of the things that students will be learning about in this unit is exactly what food deserts are, where are these areas that people are not able to get fresh foods, what exactly is hydroponics, how do plants survive, especially once you take soil out of the equation, how do different types of hydroponic systems function, how can hydroponics provide fresh food for people in urban environments, and pros and cons of using hydroponics versus traditional farming. The food desert is a term that identifies areas that are located more than 1 mile from fresh foods, and often people in these areas are forced to only live off limited pre-processed foods they can get at the convenience stores near them. One potential solution to this problem of food deserts that is taught in this curriculum is hydroponics. Hydroponics is the ability to grow fresh foods in small systems without the use of soil that can be designed to fit in smaller apartments, or as the Grand Design Challenge creates, is the use of hydroponics on the vertical sides of buildings. There are many different ways to create a hydroponic system, several which are clearly explained in the teacher documents within this curriculum. Also, how hydroponics differs from traditional farming and the pros and cons between traditional farming and hydroponics. In KSB 2, the students begin starting to design the first part of their hydroponic system, which is the structure, to hold all the parts of the system that all the plants will grow in. The students will be designing a structure within a given set of criteria and constraints. This project is set to be run with the students working in groups. The size of the groups often depends on your classroom situation and the number of kids in your class, but my normal groups are around 3 to 5 students per group. The students first individually come up with their own ideas. They start off sketching them out on paper. The isometric paper that you can see here is a good way to have the students be able to draw accurately and actually measure the different lengths of the pieces that they're going to be using in their designs. One of the requirements of the design is for the students to design their structures within a set budget. So each of the different materials that the students can use have a set price, as you can see here. They have to create a bill of materials, just like if they were going to go into the Home Depot or Lowe's or any store to buy these materials themselves before they were given any by the teacher to start building. Once each student individually has created their own design on paper and their bill of materials, then they go back to their group and work within this design matrix that is here. The design matrix is set to compare the requirements of each student's individual design to try to figure out which students or multiple students combined designs are the best for the group. Throughout the development of this unit, several different designs for creating the structures were tried and tested by different teachers. We had started off with just using 2x4 frames and large totes, as you can see in the picture on the left. That eventually evolved with many teachers into be doing PVC structures, as you can see on the right. I myself have downsized these structures to much smaller bins so I can have more systems. I usually end up with around 20 to 25 systems in my classroom. Last year I also got these metal shelving so I could set up 2 rows of them to get everything in a much more compact area. The PVC material is also much easier to reuse and assemble and disassemble by the students than the middle school students driving screws through 2x4s. Getting into KSB 3, the students are going to start building and designing their systems to actually grow the plants out of. This is made up of several different parts, which are all included in the teacher guide. Depending on which type of system the students are doing will depend on the materials that are needed. There are several versions of systems that are explained clearly in the teacher guide, but there are also many more resources on the internet if you want to spend time to search more to get other options. At this point, since I've been doing it for so long, I've made some changes to the systems I offered to my students, but some are a little more complicated than the beginner ones that are shown in this unit. 2 of the systems that are shown in this unit are the aeroponics systems and the ebb and flow systems. Both good ways to have the plants grow, but the systems are designed differently, so each student will have to have some different materials. Here you can see 2 different types of systems. The one on the left is an aeroponic system where the mister nozzles spray the roots of the systems. The one on the right is considered a nutrient film technique where the water runs down past the plants and the rock wool to give them the nutrients and water that is needed. Here you can see some of the supplies that are available for students. Some of the supplies in the teacher guide are a little bit different, but I wanted to show you some of the modified ones that I put just to show there's some flexibility to it. It's easy for me to get 5-gallon buckets, and I got the smaller totes to make them smaller sized units. Then I've also used some things with water bottles to have the kids do reclaim types of systems. Again, I set prices to each material, so they have to design within a budget. But the materials that you use to build the systems can be changed, varied, and depending on what you have. Getting into KSB4, the system and the structure should all be set up with water tested to make sure everything accurately works. The plants should now be starting off growing. At this point, the students are going to be having to record and adjust the nutrients and water and pH in their system every day or every other day. There's multiple ways that you can test all of these things with the yellow meter that's on the left. There's also the paper sticks that you can put in the water. Multiple different types of nutrients that are available online or at local stores that you can use in your system. As they are monitoring things, there's multiple different options that teachers can have the students do. There's one example here of a hydroponics data log where each time the students check it, they do a little sketch of what the plant looks like, how much it grew, the nutrients, the pH, that's all in the water for the plants to be growing out of. From there, the teacher can decide what they want to have the students do with this, whether they want to graph it and analyze it, or just have it in a data sheet to move forward with. KSB 5 gets into using modeling software, CAD software. If that's something that you already do in your program, I know some teachers may pass over this KSB since they've already taught their students, but if that's something you've never done in your class before or aren't going to be doing before you get to this unit, this KSB goes over a lot of different ways that you can teach 3D CAD drawing to your students. We focused on SketchUp in this unit. There's several different SketchUp tutorials that are available here. In my class, I usually use Inventor now. The first year I used SketchUp, but Inventor and Autodesk products are free for schools, so I prefer to use that. It's a little more advanced, but SketchUp may be a good area to start with. The tutorials go through building multiple different types of buildings and types of chambers that your systems may be designed around. The final part of this whole project is the Grand Design Challenge, which takes all 5 KSBs that we already went through, adds them all up, and the students are going to be following the informed design process to complete one final design challenge. This final design challenge is given to the students in this letter that is shown here. It's a letter that's designed to be sent from a community council asking the student's company to design a hydroponic system that can vertically be mounted on the side of the building in the city. The city areas often don't have much space for farming and also don't often have much fresh produce. So this solution will use the limited space that's there to create fresh produce. The Grand Design Challenge is also going to be done and designed within a set criteria and constraints. It's recommended that the teacher works with their students in their class to have them just figure out what the best criteria and constraints for their design is going to be. You can see here some of the ones that have been come up with some classes. Also an example that points out where all these criteria and constraints are. Once the students have designed a 3D model and put a whole presentation together, they have to give their presentation to the class to try to sell why their company is going to be the best company to choose for the community council to have design and build these vertical grow systems in the city. I know some teachers had their students come in all in business apparel and present in front of school admins. In this case, I just had the students presenting to their class as the community council. And the students themselves gave peer reviews of the presentation to evaluate each other. Included in this curriculum is all the list of materials and supplies that any teacher will need, especially those who have never had any experience in hydroponics before. There's more than enough information to get you started. One of the feasibility teachers, Corbin, put a whole bunch of information together to get any teacher, whether you've experienced it or not, a bunch of useful tips to get you well on your way into hydroponics. So there's plenty of information to get you started in there. This page is one example of some sourced materials and different places you can get stuff that we used for a lot of our curriculum. So that's basically the overview of the food unit. There's my contact information and email. If you have any questions along the way as you're trying to do this or before you get into it, please shoot me an email. I'll be more than happy to answer you or send you pictures or anything that you need. Up next we have Matthew Plummer going over the water unit, so please stay tuned in and go through the water unit with him.
Hello and welcome to this unit of the Engineering for All webinar. This is Water, the World in Crisis. My name is Matthew Plummer. I'm a technology and engineering education teacher from Davidsville, Pennsylvania, and I teach at Conemaugh Township Area School District. I'm going to give you an in-depth look at the water unit. As Matt stated before, the first 4 days are to get students accustomed to the EFA curriculum and engaged in the informed design process. A KSB stands for Knowledge and Skill Builder, and throughout this unit, students will first be introduced H2O for Life, KSB 1, KSB 2, Turbidity Matters, KSB 3, Heavy Metals, KSB 4, Clean Up Your Act, and finally the Grand Design Challenge. In the Grand Design Challenge, students will apply each knowledge and skill built throughout this curriculum. KSB 1, H2O for Life. Each one of these KSBs start with some type of big idea. In KSB 1, the big idea is the availability of safe water for drinking purposes and other uses is critical in many areas of the world. In KSB 1, students will take a look at where water comes from, the different types of water, and how the population of the world has continued to grow. In KSB 1, students have an activity entitled Where in the World is the Water Crisis? In this activity, students will examine the different types of water scarcity, including physical scarcity and economic scarcity. Students in this activity will design a brochure and then present them to the class. During KSB 1, when students learn about different types of water scarcity, it instantaneously creates empathy for design. Through my experience with KSB 1 and throughout this entire EFA activity, students are engaged because they believe that they are doing something to make a difference and contribute to the world. KSB 2, turbidity matters. The big idea, the measure of turbidity is key to test water quality. Throughout this KSB, students will examine what turbidity is and how to measure turbidity. Now that students have examined turbidity and different ways to measure turbidity, the student activity is then for students to build a turbidity tube. In this brief video, you will see how students build a turbidity tube and then test water for turbidity. KSB 3, heavy metals. The big idea states, all drinking water contains some contaminants. Some are harmless, and some can make water unsafe to drink. During KSB 3, students will examine different contaminant types along with different types of bacteria. Students will learn that not all bacteria is harmful. They will also examine where these different types of contaminants come from and what type of contaminants there are. KSB 3, students' activity is a jigsaw activity. The missing pieces of water contaminants. Students will examine water pollution versus water contamination. In the illustration above, students will examine where different contaminants come from and the difference between both of them. KSB 4 is entitled Clean Up Your Act. The big idea. Water sources can be improved by using engineering methods to remove contaminants. During this KSB, students really dive into the exploration of water, the world in crisis. Students are engaged in hands-on activity through this KSB. also exploring different methods to filter water and also different methods to test water. In KSB 4, the student activities test water and treat water. First, students examine and test the water for different contaminant types. During KSB 4, students are required to use the turbidity tube built in KSB 2. Students then, after testing the water, will develop some type of filtration system to filter the water. During this activity, I typically had students test different material types that were found local around our school. After students design some type of filter and filter the water, they then must treat the water. In this KSB, it gives different example types of how to treat water based on the contaminants. This activity tends to be a lot of fun for students because they're up moving around applying the knowledge that they have learned in prior KSBs. Now that students have acquired the knowledge and skills to test water, treat water, develop some type of filtration system, students are now given a Grand Design Challenge. This Grand Design Challenge is entitled Operation Safe Water for Bangladesh. Students are given a letter which states that they must design a water filtration system for Bangladesh. During this, students use the informed design process. Part of the Grand Design Challenge requires students to use materials native to the country Bangladesh. This group activity is an example how students use the informed design process. As you can see, students are required to describe different specifications of the Grand Design Challenge along with constraints. A group activity prior to building anything requires students to do a plug chart. The device has to be a multi-system device with 2 or more components. Must be capable of removing contaminants. It must be easy for locals to clean when needed. Made of native materials, no cost, and 2 requirements of their choice. Now that students have answered a series of questions throughout their design journals, they are now permitted to make a prototype. Throughout this process, students are extremely engaged and are excited to make a difference. They honestly believe that they are engineering to make a difference. Next, I'm going to show you a video, 2 students' solution for Operation Safe Water for Bangladesh.
I'm Emily, and we're doing the water filtration system for Bangladesh. What it is we have a water filtration system, and we have dirty water, and it's supposed to filter out the nasty Nesquik and create clean water. We recorded everything in our journal that we did, and we had 6 days to do our project. We've been working on it multiple periods a day. And we were only allowed to use a limited amount of materials such as disposable cups, water bottles, buckets, rubber bands, etc. So right here we have dirty water, and when we put the dirty water in, well, first we test it through the turbidity tube, which measures the NTUs, which is how clear it is. And we also test the TDS to see how good it is to drink. In the water filtration system, at the top we have a cloth. There's rocks, carbon, and sand, and then it goes through a cup, which is hot glued to another bucket, and there is fabric on the cup. So, and before we test it, we already have done this, but you clean it out with clear water, and then it goes through and filters out the stuff from before.
And that will conclude the water unit, the world in crisis. Thank you for tuning into this webinar. I really hope that you go out and try EFA. It is a ton of fun, and as stated before, students are engaged and believe that they are engineering for social good. At this point in time, we are going to open this up for a little Q&A with myself, Matthew Plummer, Matthew McGuire with the Food Unit, and Michael Hacker with Hofstra University.